Hi everyone, welcome to our talk. Today we're going to talk about NTLM, reflection attacks, a story of an accidental Windows RCE. My name is Wilfried. I'm with my colleague Guillaume. We both work at Synactive and doing red team and pen test assessments. So let's talk about the vulnerability. A specific CVE came out this year in June with a CVSS score of 8.8 and was classified by Microsoft as a Windows SMB client elevation of privilege vulnerability. We are not agree with this qualification. We mostly think this is a remote command execution. Actually, this is a trivial logical vulnerability that allows authenticated user to perform remote code execution. It involves authentication reflection attacks, and it was working only on machine that does not require SMB signing, so basically every Windows version except the latest one. The vulnerability was so trivial to discover and to exploit that it was independently found by many researchers. At least 7 people or company reported to Microsoft within a short period of time. Shout out to Red Team Pen Testing that were the first to discover it. I'm also wondering how many people find it and exploit it by accident without realizing that was a bug. You will see why later on. Few words regarding research motivation. I was performing some research regarding reflection attacks, and we already know there's few bugs related to this kind of attacks. For instance, our security researcher last year mentioned that Kerberos relay is way more powerful than NTLM relay, and he showed last year at Black Hat Asia a special case regarding Kerberos reflection targeting ADCS environments. NTLM reflection attacks has also a long history of reflection bugs. The first vulnerability came out in 2008, 2009 also, 2015, and 2019. And since then, we thought that NTLM reflection bugs were no longer a thing. But it was not the case. So before digging into the vulnerability, let me give you some core concept so everyone can understand properly. The first one will be authentication coercion. Authentication coercion is when you force an identity, that could be a user or a machine account, to authenticate to a control server. There are several ways to coerce a machine into authenticated to a given server. Some are deterministic, others are not. The most popular one is to force an RPC service to access to a file on an arbitrary file share. So let's illustrate that. On top we have our target machine, and on the bottom the attacker laptop. When we perform authentication coercion, we perform an RPC call, we interact with the dedicated RPC service, and there's few functions that could allow us to perform this kind of attack. For instance, EFS RPC encrypt file server. And as an argument of this function, we will specify a remote file using the UNC convention path that points to our attacker IP. Within the machine, the RPC service will talk with the SMB client. It will talk to the SMB client to interact with this file, again by specifying a remote location. The SMB client will connect back to the attacker laptop. The attacker laptop will host a SMB server, and it will ask the SMB client to authenticate. Then the authentication workflow continues, and the SMB client exchanges with the attacker laptop, and you receive an authentication blob. This is authentication coercion. Next concept is authentication relay. Relay is when you somehow force a client to authenticate to a control destination, and then you relay the authentication to another server in order to impersonate the relay identity. So the start is the same. We force the authentication, we receive the authentication blob from the client from machine A, and then we relay this authentication back to the service on machine B. This way we are authenticated on service B as the client from machine A. Next concept is authentication reflection. This is a special case where the authentication relay, where the client and the server are on the same machine. It was previously classified as a bug by Microsoft, and mitigations were in place to prevent relaying back the authentication to the same machine. But basically the workflow is the same, except it's on the same machine. Last concept will be Kerberos authentication coercion. We already know that NTLM relay attacks are easy to exploit, but it's actually more difficult regarding Kerberos. The main difficulty is to receive a Kerberos authentication, which is an IP rec message, to a control IP. Kerberos uses ticket with SPN for service principal name with the following format. First is the type of service, CIFS, following by the destination, SRV1 here. The SPN is constructed by the clients based on the server host name or fully qualified domain name. Server host name or fully qualified domain name is resolved through the DNS, and in that specific case, DNS is not under our control. So it's actually harder to perform Kerberos authentication coercion. If I'm illustrating that, from our attacker laptop, we perform coercion. We said, please authenticate to SRV1 to our target, here SRV1. The machine will ask to the DNS server what is the associated IP address. The DNS server will answer with the proper IP, and it will be within the same machine, so we don't receive any authentication message, which is an IP rec. We thought that Kerberos relaying was way harder until James Forshaw, a well-known security researcher, discovered something very interesting. He found that a Marshall credential target information structure can be added at the end of an SPN. And during the authentication process, LSASS will discard it before making Kerberos ticket request. How does it work? When we're trying to request a ticket for CIFS/our target SRV1, followed by the specific base64 encoded structure, which is the credential target information, it will actually return one for CIFS/SRV1, the SPN that we want. And also, one thing to note is that the specific structure, SRV1 following by the base64 string, is a valid DNS record. So how can we exploit that? First, we register the specific DNS record. For instance, on Active Directory environments, any authenticated user can edit the specific record. We then coerce a machine into authenticate to that specific DNS using the SMB protocol, and then we can receive an IP rec message for the SPN that we want. Again, let's illustrate that. First, the attacker adds the DNS record. It points to his attacker machine. Then we perform authentication coercion to SRV1 following by the credential target, the Marshall credential target information structure. The SRV1 will ask the DNS server what is the associated IP tied to this specific record. It will answer with the IP of the attacker. And then we can receive finally the authentication blob, which is an IP rec for the SPN CIFS/SRV1. Okay, this is Kerberos authentication coercion. So now let's talk about the vulnerability discovery. We know that some check or protection against reflection may be based on names. So we try to fiddle with the target name during coercion. I was performing some reflection attacks researches, and something interesting happened when coercion to that specific DNS record happened. To do so, the first step is to trigger the authentication. It can be done with petit potam, using a low privilege account, and I'm using, again, this specific DNS record that are already registered. It points to my attacker IP. To perform Kerberos relay, you can use the dedicated tool krb relayx.py, which is from Impacket. And when receiving the authentication, I got this weird error message that is saying unsupported make type NTLM SSP. I was quite confused because here in that specific case, when performing the coercion, I'm not using any IP address, I'm only using hostname or fully qualified domain name. And most of the time, Kerberos is preferred within Windows environments. So I was a bit confused, and I'm asking myself what it's trying to do NTLM. So I want to debug that and to perform network analysis. And instead of using the tool dedicated to Kerberos relay, I will use NTLM relay X that is useful for NTLM relay. So the first command is the same, I'm triggering the authentication. And then when using NTLM relics, something interesting happened. First, the authentication succeeds where it shouldn't be, and then it gives us a privileged SMB session. Here, in that specific case, NTLM relics by default dump the registry hives, here the SAM hashes we contain for the local account. So at first, I was a bit confused because normally reflection attacks won't work, and I already know that there's some specific registry keys that we could set that allows to perform reflection attacks. But in my environment, this specific registry key was not set, so it was the default configuration, and I was surprised. So I quickly asked another colleague, and I told him, I got this weird behavior. Can you confirm that on your own environment? He was thinking I was bluffing. He said, okay, he was thinking like it's not possible. He must be bluffing. So before answering back, he tried on his own environment and told me, okay, actually, what the fuck, it's working. So basically, this is how we discover accidentally this vulnerability. But we cannot let things like that. We have to understand why does it work, what is the root cause. So while I was performing the relay, I used Wireshark to perform network analysis, and I want to perform some network diffing. And I wanted to compare when we tried to coerce the authentication using an IP address, pointing to my attacker IP, and compare with using that specific DNS record. And I noticed few changes during the NTLM SSP challenge message type. That is, few things that change. On the left, there's a specific flag that is not set, and also a field which is called reserved that is empty. On the right, when I'm using the specific DNS record, that specific flag is now set, and the reserved field is not empty anymore. It has a value. In fact, on the left, we are performing standard NTLM authentication, and on the right, we are performing local NTLM authentication. The specific flag is dedicated for negotiate local call. So we have to understand what is local NTLM authentication. Local NTLM authentication will work like the following. First, the client will perform initial security context. Everything is within the same machine. We are performing reflection attack. It will discuss with LSASS and the dedicated provider, here NTLM SSP. The NTLM exchange will now start. The NTLM SSP will answer back to the client. It will send the NTLM negotiate message, and then the client will forward this NTLM negotiate message to the service. Then the service will perform accept security context, still during the NTLM negotiate message type, and within the memory of the NTLM SSP, it will create a context and specify this context within the memory of the NTLM SSP within a local context list. It will be identified with a specific ID, for instance, here 10,002. Moving on during the authentication workflow, the NTLM SSP will answer back to the service. It will perform the NTLM challenge, and within this message, the context ID will be specified. And then the service will answer back to the client, and this is where the service tells the client to perform local NTLM authentication. Within the NTLM challenge, the specific context ID is not specified. This is the value that was in the reserved field, and also the flag that was set, which stands for negotiate local call. Moving on, now the client knows that he has to perform local NTLM authentication. He will perform initial security context, and will forward the NTLM challenge to the NTLM SSP. And using the context ID, he can now, within the memory, add the token handle to the client. So now, within the memory of NTLM SSP, we have a specific context ID with the token handle to our incoming client. The workflow continues. We are now to the NTLM authenticate, the last part. Basically, the NTLM SSP answers back to the client, and the client forwards to the service. This message is almost empty because we are performing local NTLM authentication. And the final step will be the service that we'll discuss with the NTLM SSP that will again call accept security context. And now it will use the context ID within the memory. It will find it. And because it's find this context ID, the authentication will succeed. And it can use the token handle of the client to impersonate this client on the service. So, in conclusion, we are relaying a local NTLM authentication over the network. But why does the server decide to perform local NTLM authentication? Why does the specific flag is set when we are performing network analysis? In order to understand, we have to dig into the SMB client authentication workflow. First, we are using our SMB client. We want to connect to the specific SPN, CIFS, SRV1, following by the structure. The SMB client will perform initial security context. It will discuss with the ksecdd driver within the kernel. Then this driver will perform an RPC call to LSASS. And this is the most important thing, where LSASS will discard the credential target information structure by performing LSAP check marshal target info. So this is where our SPN will become CIFS SRV1, following by the base64 into CIFS/SRV1. And then LSASS will discuss with the dedicated provider, here NTLM SSP. Okay, so we can use something that we are calling NTLM client local authentication hinting. Basically, the client will hint the server to perform local authentication or not. So let's illustrate that with a few examples. Previously, when we were trying to perform reflection attacks using the IP address of the attacker, it has the following workflow. The SPN will be with the following format, CIFS/the IP address. The IP address will be isolated by calling SSPR get target host name, and now few choices will be made. The first one will be, is the target either the host name of the machine, the fully qualified domain name, or the specific string localhost? In that specific case, it's not, so we move on to the next check. Is the target, or target IP, one of the local IP addresses of the machine? Again, here it's not the case. This is the attacker, the IP pointing to our attacker machine. So now the client does not hint the server to perform local authentication. On the opposite, now we are using as SPN with the following format, CIFS/SRV1. We isolate the target, that will be SRV1, and the same checks continues. Is the target either the host name of the machine, the fully qualified name, or the specific string localhost? Yes, in that specific case, SRV1 matched the host name. Moving on, few checks are now performed. Are we requesting a new session? No, we did not. Then are we providing explicit credentials? Did you provide a username and a password? We did not. So now the client needs to hint the server for local authentication. When we are performing network analysis, now during the first step, during the NTLM negotiate message type, we can also notice a few different things. On the left, when we are not hinting to the server to perform local authentication, we can see that the calling workstation domain and the calling workstation name fields are empty. On the opposite side, when the client is hinting the server to perform local authentication, those two fields are now filled with the domain name and the name of our target, here SRV1. So in order to summarize, when you are performing NTLM reflection, we know that LSASS discards the credential target information part of the target. Again, our specific crafted DNS record, SRV1 following by the base64, becomes SRV1. The NTLM SSP client identifies that SRV1 is the local machine. It will then hint the service to perform local authentication. And then the NTLM SSP server decides to perform local authentication. And then moving on, it will fill the reserve field at the specific negotiate local call flag, and then the authentication will now succeed. There's still one question that remains. Why are we privileged on the machine when the relays succeed? In fact, the SMB clients run in the system process, and that process runs as an anti-authority system. The SMB server can therefore impersonate the token of the anti-authority system, which has allowed us to perform any arbitrary action on the machine, for instance, dumping registry hives. We can illustrate that with a quick demo. On the top, I will start the NTLM relic server, and here I will using the -e option in order to execute an arbitrary binary. It will be a reverse shell to our attacker IP. So basically, I'm setting up a listener on port 443, and on the right, I will perform the authentication coercion using a low privilege account using a specifically crafted DNS record. Here, workstation 1 following by the base64 string. So I will trigger the authentication. I will receive the authentication on the left on NTLM relics. The authentication will succeed. Because I want to execute a specific binary, it will try to find a network share. It will find the admin $share. It will upload the binary, create a dedicated service, and we will receive an incoming shell. And we can see that we have the anti-authority system identity on the workstation 1 machine. Now I will let my colleague Guillaume talk about other things.
Okay, so now that we have successfully demonstrated the attack, the reflection on NTLM, and explained why it worked, we also wanted to take a look at Kerberos. If you remember, at the beginning of the talk, we told you that when we first tried to fiddle with authentication reflection, we first tested it with Kerberos, and we got a strange error. The error was that we received an NTLM authentication instead of a Kerberos one. That seemed weird to us because, as you may know, Kerberos is the preferred authentication protocol in Windows systems. And at the time, we thought that all the conditions were met to perform a Kerberos authentication. So the question is, why were we receiving an NTLM authentication? So the first thing to note is that the SMB client uses the negotiate SSP to perform authentication. It's a special SSP that selects between Kerberos or NTLM depending on what the server supports. What we thought, and what is true but with some details, is that Kerberos should be prioritized. So here, what you see is the decision diagram that we thought was the one used by negotiate workflow. The first question to ask is, does the target server support Kerberos? If the answer is yes, the SPN that is requested by the client must also exist in the Active Directory. If it is yes, we thought that Kerberos was going to be used. This diagram is actually incorrect. It is missing one check, which is a check that you already saw in the presentation. It's the following. Is the target either the host name of the machine, the fully qualified domain name, or the string localhost? So now, if we take our example, we coerce a machine to authenticate to the DNS record with the base64 data. The base64 data is stripped off in LSASS, so the negotiate SSP received only CIFS / the name of the machine, here SRV1. We go through the first check. Does the target server support Kerberos? Here the server is Kerberos, so yes, it supports Kerberos. Then the second check, is the target either the host name of the machine, the FQDN, or localhost? It is also true. SRV1 is the host name of the machine. And now the third check, does the target server support NTLM? And actually, what we didn't know at the beginning is that KRB RelayX also advertises NTLM as one of its MEC type. So the answer is yes for this check, and now you can see on the diagram that NTLM is chosen by the negotiate SSP. So basically, Kerberos is always prioritized, except if we're doing a local authentication. So can we do something about it? The answer is quite simple. We just have to change the result of the last check. We just have to remove NTLM from the MEC types advertised by KRB RelayX. It's just one line to change in the source code. And after doing this, we rerun the attack and found out that the reflection also worked for Kerberos. So it worked like this. First, we coerce the machine into authenticated to our server by using, of course, the DNS record with base64 Marshall target information data. The SMB client asks LSASS to generate an AP rec and sends us the AP rec. As you can see, the client of the AP rec is the machine account, SRV1 and the SPN is for CIFS SRV1. We take this AP rec, we relay it on the SMB service, and the SMB service gives us a privileged SMB session. If you know a bit about machine accounts, this should be a bit weird to you. A little reminder, the SMB client runs as NT-authority system. When network authentication happens with this account, the authentication is actually done with the machine account. So if you try to access a remote share, if your process is running a system, you will authenticate as the machine account. So basically, we are relaying an authentication of the machine account. And what is weird here is that the machine account should not be privileged on its associated machine. So why does the reflection give us a privileged SMB session? To understand this, a little bit of reverse engineering was necessary. What I will present now only applies when the client that is performing Kerberos local authentication is NT-authority system. It's a bit different for other accounts, such as domain accounts, and I will not talk about it in this talk. So as usual, the client begins with an initialized security context. This time, it will be forwarded to the Kerberos SSP. The Kerberos SSP will first create what is called a subkey entry, which contains various information about the client, such as the LUID, which represents the logon session, which is always 3E7 for system. It will also generate a random subkey, and it will also store a token handle to the token of the client, which is a system token. And after that, it will insert this subkey entry into a global subkey entry list that it maintains. Finally, it will forge an AP rec message, and it will include the previously generated subkey into the AP rec that the client will receive and forward to the service. The service will call accept security context and provide the AP rec that it received previously, so that the Kerberos SSP can check the AP rec. The Kerberos SSP will decrypt the AP rec, and it will check in its subkey entry list if one of the entry matches the subkey that is stored inside the AP rec. If it does, it will conclude that the AP rec is correct and that the client is identified by the token handle in the subkey entry. It will return success to the service, and whenever the service will want to impersonate the client, it will actually impersonate the token handle that was stored previously. In our case, the token handle is a system token, so that gives us a system session via SMB, which is privileged, which allows us to perform administrative actions. So that wraps up what we researched on NTLM and Kerberos. But actually, we wanted to talk a bit more about additional primitives that were found a bit later after we published our research. And that provides also interesting attack primitives, even if you cannot relate to SMB. So after the research was published, user named CTGF later opened an issue on the Impacket GitHub repository, stating that according to its test, NTLM reflection seemed to bypass channel binding for some protocols. In case you don't know, channel binding is a protection similar to SMB signing, but for TLS-based protocols, so HTTPS, MS-SQL, LDAP over TLS, etc. It seemed to work for HTTP-based protocols, which includes WinRM, and also for MS-SQL. And what was really interesting is that it seemed to work even when the channel binding token hardening level was set to strict. Strict in this case means that the server requires it, so it should not be possible to perform a relay attack when the channel binding hardening level is set to strict. So we decided to dig a bit, and by reversing the NTLM client, we noted that the channel binding token was actually not checked at all if NTLM local authentication was performed. So that was a specific case where it was not checked at all, and it is the exact same case that we presented previously. This is why the relay worked even when the channel binding policy was set to strict. We also found out that the vulnerability was actually reported by Live and fixed in CVE 2025-53778, which was published in August. The checks are rather simple, the additional code. In SSPR handle challenge message, which is the function called by the NTLM client, the channel binding token is computed, if applicable, and stored in the authentication context. And afterwards, in SSPR handle authenticate message, the channel binding is extracted from the authentication context and compared with the expected value. If the value do not match, then an error is triggered, whereas before it was not checked, so authentication was successful. What could you do with this at the time? Now it's fixed, but before you could use it. The first thing that comes to mind is exploitation of ADCS, Active Directory Certificate Services, which is the PKI of Microsoft, which can expose a web service that can be used by users to request certificates. This service is well known for being vulnerable by default to authentication relay, but can be hardened by enforcing HTTPS and channel binding. But in this very specific case, you could bypass the channel binding even if it was set to strict, just by performing a local NTLM reflection, just as we presented earlier. So the workflow is the following. You trigger an authentication with Petit Potam with the DNS record, and you relay the authentication to the HTTP service of the ADCS to request a certificate as the ADCS server. With this certificate, you can request a Kerberos ticket, and with other Kerberos shenanigans, you can basically convert it into an RCE on the ADCS server. If you get RCE on an ADCS server, basically it's game over for the domain, you have compromised it. So that was an interesting vector. Another one that was interesting was that you could relay to WinRM over HTTPS. As you know, WinRM is kind of an equivalent to SSH for Linux and allows you to execute commands on the system. So via this vulnerability, you could coerce any machine to authenticate to you via the base64 DNS record and relay back the authentication to the same server if it exposed WinRM service over HTTPS and get remote command execution as system. So that was basically an alternative to relaying to SMB. So the last part of this talk will be about the patch that Microsoft issued. When Microsoft published the patch, we were kind of curious to how they fixed the bug. Did they fix it by issuing a patch for each protocol, one for NTLM, one for Kerberos? Did they manage to issue only one patch? So the question was where to look for. Actually, in the advisory, Microsoft labeled the vulnerability as Windows SMB clients elevation of privilege vulnerability, which seemed to indicate that the patch was in the Windows SMB client, which is partly implemented in ArmorX smb.sys, which is a driver. So we perform a quick patch diff and saw that actually only one function had changed. The SMB-CE create SRV call function, which is called when the SMB client is trying to access a resource over SMB. And the patch is actually quite simple. The SMB client, before establishing any connection to the target, will call cred and marshal target info to check whether or not marshal credential information is present in the target name. So basically, it will search for the base64 data in the target name. If it finds any, it will abort the connection. So what does it mean? Basically, it just kills the primitive or coercing arbitrary machine into authenticating via Kerberos. So the step that is blocked by this patch is the step with petit potin. And finally, a small conclusion. By doing this research and this presentation, we wanted to highlight that high-impact, simple, and stable logical vulnerabilities still exist in Windows systems. We also want to note that SMB signing is still underrated. For example, it would have prevented exploitation of this vulnerability for the first scenario that we talked about, which is SMB to SMB. Of course, it wouldn't have prevented what I just talked about HTTPS and WinRM, but it actually required another vulnerability. And what is to be noted also is that SMB signing is still not enabled by default on Windows systems, except on Windows 11 24H2. And finally, the last crucial remaining questions. Is it the end of authenticated reflection vulnerabilities? Well, no, but maybe that will be for another talk. Thank you for listening.